Okay, so what is stoichiometry? Stoichiometry is the mathematical or quantitative relationship between products and reactants. It's a molar relationship, not a mass relationship, molar relationship. That means if the given is not in moles, convert to mole. And that goes right along with the 4 steps of solving a problem in here. Step number 1 is balance the equation. What's given? What are we trying to calculate? And then there's the setup. Okay? Now, I had a funny story about this. I used to teach a class very similar to this up in Tacoma. This is like 15 years ago or so. And the test was on stoichiometry. So the name of the test was stoichiometry test. And I needed 5 points to make the points come up to 100. So I just said, what's the name of this test? And only half people got it right. At the first page, the name of the test was stoichiometry test. It was just like, anyway. Okay. All right. So let's look at a typical stoichiometry problem. All right. Up until today, all we've done is conversions on something that's not changed. All we've done is rename it. Today, we're giving you something, and then we're asking about something else. And there's a reaction that happens. So that's why we're balancing the chemical equation, is for that reason. Okay, 15 grams of water is formed. How many grams of methane is consumed? This is if we're burning methane, combustion. Okay, so first of all, you need to, what is the chemical reaction? Now, in 1A, and it depends who you get in 2A, this is all you're going to get, and you have to come up with your own equation. And here, I'm going to give you the equation. Unbalanced, but I'm going to give you the equation. So methane is CH4. We're burning it in oxygen. That gives us water and carbon dioxide. What's going on? Okay, so tomorrow when you start your car in the morning, I want you to run around, get out and run around to the back and look at the tailpipe and see what's coming out of the tailpipe. You're going to get a liquid come out of the tailpipe. Guess what the liquid is?
I don't have a car. What tailpipe do I use? I mean, I could think of one, but I don't think it's one.
Who knows? Yes,
Water.
water. Because what's happening inside your engine is combustion, which is this equation here, only instead of CH4, it's C8H18, which is gasoline, octane. Now, after a while, after like 5 minutes, when you run around and look at your tailpipe, is the water still coming out? Liquid water's not coming out, but gaseous water is. And the reason why it's gaseous is because the tailpipe is nice and hot now, turns the liquid water to gas. So you're still producing water, it's just that it's not in the liquid form. Okay. Have you ever noticed up in the sky when a jet goes over, what's in back of the jet? Huh?
And
Chemtrail. Okay, some people call them contrails, CON. If you're Art Bell, you call them chemtrail. Who's heard of Art Bell? Anyone? He was murdered. He was a early talk show host that did controversial stuff on AM radio. And usually it was around midnight. I used to travel a lot when I was at IBM, and I would so I listened to in the middle of the night. Anyway, who knows what the white stuff is coming out the back?
some people think it's mind control.
That's right. Art Bell was talking a lot about that, actually. That's why you reminded me of Art Bell when you said chemtrails.
It's vapor.
What kind of vapor?
A combustion of gas, oxygen.
Okay, so look at the equation here. This methane here. If methane plus oxygen gives us H2O plus water. Instead of methane, let's burn jet fuel, which is basically kerosene. There's no difference in the output. You still get water and carbon dioxide. So, what's the white stuff coming out of the back of the jet?
Steam.
If we were up at 30,000 feet, how is it hot or cold up there? Very cold. I mean, cold, cold. During World War II, B-17 bombers and B-24 bombers had no insulation. So everyone had to bundle up big time because it was so cold, and they had to work guns and all this stuff. Very, very, very cold. So what does the water coming out of the jet engine do at 30,000 feet? Yeah, cools to ice. So what you're seeing are ice crystals coming out of the back of the jet. And if you look really, really closely, the ice crystals don't start right away because there's gas coming out of that. Jet engine is very, very hot. It's like 900 degrees. So as they come out, they're gas, and all of a sudden they go to liquid, then they solidify to gas, to ice crystal. Anyway, that's a contrail, a product of combustion. Okay, so step one is write the reaction, and next is to balance it. Is this balanced? Let's do an inventory. Okay, carbons 1 and 1. Hydrogens 4 and 2. And oxygens 2 and 3. Okay, is it balanced? No, we need to balance it. Okay, so let's put a 2 here. That'll kick that up to 4. Okay, that changes the number of oxygens now to 4. Okay, oxygens are not balanced, so we need to put a 2 out here. I'm going to restart this. Okay, it's balanced now. So how do you know it's balanced? Because carbons are equal on both sides, hydrogen's equal on both sides, oxygen's equal on both sides.
Yeah. It
No,
or
I,
we-
okay. Step number one, assume all equations I give you are unbalanced. If on your dry lab today, I did balance one equation for you, but that's problem number two. Because that is hard to balance. I didn't want you to spend a half an hour balancing it. I just balanced it for you. All the others are unbalanced, except for problem two. That's why I want you to do that one last, because it's the hardest. Okay, so we got the balancing done. All right, so what's given? 15 grams of water. Notice I put the water above the 15 grams. Okay, now I'm going to be doing this without parentheses. I'm going to do it using something called railroad tracks. Most people use railroad tracks and not parentheses, except for simple conversions. Now, every one of these I'm going to do today is 3 steps. So stoichiometry basically is 3 steps, sometimes 4. Most of the time it's 3 though. So I'm going to draw vertical lines instead of parentheses. I'm drawing a big long line because that's the fraction bar that extends all the way across. Okay, so what are we trying to calculate? Grams of methane. Okay, so the balanced equation is a molar relationship. So we're starting with grams, we got to get to moles. So if we add up two hydrogens and one oxygen from the periodic table, hydrogens are 101 apiece, so that's 202. Oxygen is 16. So the molar mass of water is 18.02 grams. Okay. So that comes from the periodic table directly. Okay, so that'll get us grams to moles now. Grams have got to cancel, moles on top. Okay, so now we have moles of water. Now from the balanced equation, we're going to do the ratio of water to methane. Okay, from the coefficients ratio. Okay, so methane is 1. Water's 2. This is why we balance the equation, this step here. Okay, so we've got now, if you go on YouTube and look at some tutorials on this, it'll be exactly the same, except for Some people put 1 mole and 2 moles here on the ratio of the coefficients, and some people don't. I don't. But if you're reading a tutorial, you might see that. There's no other change though. Everything cancels out just the way it's supposed to. Okay, so now we've got what's left here, moles of methane. So now we need to get grams of methane. So we need the molar mass again. So one carbon, 4 hydrogens. Carbon is 12.01. Hydrogens 101 apiece, so there's 4 of them. So that's 1605 grams per mole. So that's going to get us from moles to grams now. For moles to cancel, it's going to be in the bottom. Why does it keep doing? It's not cooperating.
Not like that spot.
Hmm?
Doesn't like that specific spot.
It's been doing that. I have a brand new one of these. I'm going to hook up tomorrow. Okay, so the moles cancel. Okay, so what are we trying to calculate? Grams of methane. What's left over? Grams of methane. Okay, so here are the 3 parts. First part is given to moles. Now, the given could be liters of gas. Remember, that was 22.4 liters per mole. It could be grams. That's the molar mass in the periodic table, or it could be the number of particles, which is 6.02 times 10 to the 23rd. Any of those will get you to moles. Okay, the middle part is from the balanced equation. It's the ratio of what's given to what you're trying to calculate. And given is on the bottom, so it cancels. And then once we do that, we need to go from moles to whatever we're trying to calculate. Moles to grams, moles to liters, moles to particles. 3 parts. Now, when you look at the solutions on your dry lab stoi, you look down and every single problem looks like this. So those of you who like patterns, you have a pattern. Given to moles, mole ratio from the balanced equation, and then moles to what you're trying to calculate every single time. Every single time. That's the 3 steps. Okay, so let's calculate this, see what we get. Now we're going to multiply everything on the top, divide by everything on the bottom. Sig fig wise, we got 3. 4. How many sig figs with the 1 and 2? Yes, that's right. I only saw one part. Let's see the other part. Okay, so one person said infinite, and that's right. It's because it's exactly 1 and exactly 2. There's no measurement involved. So those don't come into play regarding the sig figs for the answer. We've got 4 here, means our answer is going to have 4. So it's going to be, the answer is going to have 3, not 4. Okay, so we're looking at 6.68 grams of methane. Now, this is frequently called gram to gram stoichiometry. You start with grams, we end up with grams. Okay, so any questions about this process? Yeah. But if you look at the problem, though, it wants to know how many grams of methane. Right here. Okay, so let's do some more of these. Yeah. I'm sorry? Oh, I've been doing this for 30-something years.
Oh, it. Remember this all this color.
I would, remember I said earlier, I'm gonna give you the equation.
Oh, okay.
In your next class. But they won't give you stuff you haven't theoretically had. Methane is something called an alkane in organic chemistry. And it's just combustion is some kind of a hydrocarbon. Methane, ethane, propane, butane, gasoline, kerosene, all those burn really nicely, alcohol. But the process is you have a fuel. Live by technology, die by technology. What is this? Wow. Let's try adding a new page. Okay, so combustion, it's a fuel. In this case, it's methane, GH4, could be gasoline, it could be jet fuel, whatever, it's fuel. Plus an oxidizer. An oxidizer oxidizes the fuel elements. Then you get oxidized fuel, plus a lot of heat. Now, frequently, for example, with a shuttle, they used hydrogen gas and oxygen gas and made water. That was enough to kick that huge shuttle up into space, making water. Frequently, the oxidizer is oxygen gas. And frequently, the fuel is a hydrocarbon, like gasoline or jet fuel. That's combustion. That's one of 6 types of reactions. Combustion is one of them. By the way, that happens in our mitochondria as well, in our bodies. It takes glucose and combusts it to carbon dioxide and water, plus a lot of energy molecules called adenosine triphosphate or ATP. Okay, anyway, that's combustion. Okay, so I'm going to continue with this page. It seems to behave a little better. Let's do another problem here. Now we're going to continue with methane, so we don't have to worry about balancing another equation. Okay, 23.5 grams of oxygen gas. I guess it would be R consumed. How many grams of water are produced? Okay, so let's start with our equation. God, it's a sink.
You have a mouse active somewhere that you don't know?
I don't know. That's a good thought, though. Okay, so we have methane burning, and let me balance it real quickly. It's balanced now. Okay. So we're starting with oxygen gas, O2, and we're going to end up with water, grams of water. So what's given is oxygen gas, so we need to convert that to moles. So let's set it up first here. Okay, so step 1 is convert to moles. Step 2 is the mole ratio from the balanced equation. And then we go from moles to grams. Okay, so we need the molar mass for O2. Okay, oxygen is 16.00, and there are 2 of them. So that's 32 grams per mole. And then we have water, which we've already done. Okay, so we have 32 here. And we have 1802 here. Now, for those of you who like parentheses better than railroad tracks, you'd have that's what your parentheses would look like. Okay, one thing's left. What do you have to do? It's a mental step. So the ratio is 2 to 2. Okay, it's all done. Yeah,
What is that thing about 3,200?
mole, MOL.
Ah,
You put it either if you want. Okay, so that's a setup. And again, remember 90% for setup, 10% for answer. Are there any questions about this setup? Sig figs is going to be 3, 4, infinite, 4, 3. Okay, so let's try one with Are there any questions about this? Notice it's exactly the same as we just did. 3 steps. Given to moles. So given to moles, step number 1, ratio from the balanced equation, making sure the given is on the bottom so it cancels. Then we're going from moles to what we're trying to calculate. And this is what the second part of the dry lab is all about, practicing a whole bunch of these. And again, look for the pattern. Look for the pattern. It'll always be there. Okay, let's do another one here. Um, Okay, 23.4 liters of gaseous water is produced. How many grams of methane is consumed? Okay, so first thing is you write the equation. I'm going to use the same equation each time, so I'm going to have to balance it each time. So we're looking at methane, oxygen, carbon dioxide, and water. Okay, so let's balance it real quickly. Okay, balanced. All right, so what are we starting with? 23.4 liters of water. So what's the conversion factor going from gaseous liters to moles? Who remembers? That's the more mass. When we're dealing with gases, it's 22.4. Remember that? It's a couple weeks ago. Your mind can remember things better than mine.
It says 23, did it like add something to that?
That's what we're starting with.
Oh.
We gotta remember, step one is convert to moles. So the liter relationship in moles is 22.4 liters for 1 mole at STP, standard temperature pressure. So that's what's gonna go here. 1 mole on top, on the bottom. So that's given to moles. Given cancels. All right, next step is the mole ratio from the balanced equation. So water is going to be in the bottom. That's a 2. And methane is on the top, which is a 1. This is from balanced equation. Okay, so water cancels. Now we have moles of methane. Now we need to go moles of methane to grams of methane. Okay, so we have 1 carbon, 4 hydrogens, that's 1201 and 404. Hydrogen is 101 apiece, times 4 is 404. So we're looking at 1605 grams per mole. You know, I think it was that mouse that was somehow interfering. Because when I move the mouse out of the way, it's working fine. Okay, so this is moles to calculated. Okay, is everyone okay with the setup? Remember, multiply everything on the top, divide by everything on the bottom. Okay, we okay with this? Gee, is there a pattern emerging here? There sure is. I need to beat you on the head with this. Because they will not tell you this in 1A and 2A. I have a number of my students have told me in the past, I visualize patterns. I always mention this pattern thing in case you do too. My main thing is the setup is the same, yeah. The what? The three. Oh, sig figs. Yeah, so this is a three, infant, or okay, so I'm gonna do one more, then we're gonna break for dry lap. Use combustion of methane again. Okay, if 34.6 liters of oxygen gas is consumed, are consumed. How many molecules of water is produced? How many molecules or how many atoms? Think Avogadro, 602 times 10 to the 23rd number again. Now, in our class, whenever we mention gases, we're talking about at STP for the mole conversion. And we're gonna have a gas lab, which is a really fun lab. We're gonna take liquid nitrogen, do some things with it. It's very cool. Okay, so start with the equation again, same equation. Notice I flip-flop frequently between the water and carbon dioxide because it doesn't matter. Okay, so let's balance it. It's officially balanced. Now in the test, if I say, how do you know this is balanced? What you do an inventory. You go CHO 114444. That's how you would show me if the equation's balanced. Okay, so what are we starting with? Starting with liters of oxygen gas. First step is liters to moles. Okay, that gives us moles. Now we need to go moles to water. I mean, moles of oxygen to moles of water from the balanced equation. So that's going to be 2 again. Now we have moles of water. Now we need to go to how many molecules of water, and that's Okay. So we're going given moles. Same 3 steps. Now this problem is worth 10 points. You're looking at 9 points right now. Now, stoichiometry problems are going to be worth more raw points than conversions. Conversions are typically 8 points. Stoichiometry problems are typically 15 points. Yeah,
Are we able to just make water in the lab by combining things like hydrogen and oxygen?
mhm.
Because I mean, that just seems pretty useful, especially in California in a drought.
Well, the question is, where do you get the hydrogen from?
Yeah,
Oxygen is not a problem.
yeah,
Hydrogen gas is the problem.
yeah, so where would we?
And guess where they get hydrogen gas from?
A moon?
No, usually from taking water and breaking it apart.
Oh, okay, that's ironic, kind of productive.
So, yeah,
On the second section, where did the 22.4? Did that come from the?
that's because oxygen is a gas. So all gases at standard temperature pressure, it's 22.4 liters per 1 mole, regardless of the gas.
Oh.
So it's methane gas, oxygen gas, gaseous water, uranium hexafluoride
Yeah.
gas at standard temperature and pressure. It won't be 22.4 if it's not standard though. We're going to do standard everything until we get to unit 4. That's when we cover gases. Okay, so let me grind this thing out here. Three sig figs again. Okay, so that's basic stoichiometry. Now, stoichiometry can be tricky when you have 2 givens. But it's much trickier when you have 2 givens. 1 given, this is it. 2 givens, we have a page of calculations. Okay. Are there any questions on this last one? That's, remember, there are 3 conversions. 602 times 10 to the 23rd of anything, atoms or molecules per mole. 22.4 liters per mole for gases. And then there's the molar mass, comes from the periodic table, grams per mole. And those are the only 3 conversions you need. And then the 22.4 and the 602 times 10 to the 23rd, doesn't matter what you're talking about. It can be ducks, atoms, or molecules, just like a dozen. It can be a dozen apples, a dozen eggs, or a dozen students. It's still 12. All right. So what we're going to do is do dry lab. Okay? Are there any questions? Huh?
Is everyone?
It's the Friday people. It's like long, right? No, it's okay.